Hello again, this is David Villar, and welcome to this second presentation of pharmacokinetic considerations of non-steroidal anti-inflammatory drugs. I would like to start by saying that pharmacokinetics is one of those areas that students and veterinarians alike find more difficult to understand. It's always one of those tough bones to chew on, and beyond the concept of a half-life, nobody really finds much practical applications to real life. As I said on the first video, I'm not so interested on presenting you with all the specific details of the information on anti-inflammatory drugs here, but I would like to use these first videos to introduce you to principles that will be able to apply to most other categories of drugs, and hopefully help you design some prescription protocols. So what I would like to do on this presentation is take one or two key ideas for each one of the steps of pharmacokinetics that apply to non-steroidal drugs as a group. And as you can see on this first diagram here, what the body does to the drug from the time it enters until it becomes excreted, the steps can be broken down into absorption from the site of administration to the bloodstream, distribution throughout the body with the systemic circulation, metabolism or biotransformation, and finally elimination, or it would probably better be said as excretion. As I said on this presentation, I selected a few key ideas for each one of the steps of pharmacokinetics, and in reality they are principles that could also be applied to other types of drugs, as you will see, which is why I chose to present them as questions. The first one is how are weak organic acids better absorbed in the gastrointestinal tract? If we were to give them as a tablet, should we give them on an empty stomach with water, without water? Should we give them with food, on a fasted animal? The second question is, how does highly protein binding affects the duration of action of the clinical effects of non-steroidal drugs? The third question is, how does the liver carry out those two steps in metabolism? As we will see, this is quite important because it will determine the diverse half-lives that we see not only between different non-steroidal drugs, but also between animals within the same species. It also explains why drugs like phenylbutazone have what we call zero-order kinetics, in which the half-life is no longer a constant. And the final step is the excretion, and here we will basically say that most non-steroidal drugs leave the body as metabolites, not as a parent compound. And this is really not so important from a practical standpoint. It would probably be relevant in toxic situations, but we probably won't go into that here. So if we start by saying that non-steroidals are weak organic acids, from a practical standpoint, that means they're generally well absorbed when we give them orally. If we were to give them any of these drugs in a solid preparation, say as a tablet or a capsule, they would have to first disintegrate into smaller particles. And the second physical process would have to be the dissolution of the drug molecules into the gastric juices. In other words, they would have to become invisible drug molecules that must be into a solution, completely dissolved in an aqueous environment of the stomach. Just like when you put sugar into a coffee, it totally dissolves. And the final step is to become in contact with the membrane of the cells, and obviously cross inside into the bloodstream. And this is usually done in the intestines because the stomach doesn't really have enough surface contact to do enough absorption. So the longer the drug stays in the stomach, probably the slower the absorption process. If we look at this picture of the intestine, we can see that the surface contact is much greater in the intestine compared with the stomach. At least 600-fold bigger contact area. And the other consideration is that the microvilli that surrounds the enterocyte is basically a water environment, which means that the drug must be in a water soluble environment also in order to get to that membrane and cross into the lipid barrier before it penetrates. So why is this all important? Well, most drugs don't really have a problem because they're going to dissolve very well in those gastric juices of the stomach. And as I just mentioned, those three steps that I just alluded, the limiting step is really the absorption, which is the last one. So if we give the drug with water in an empty stomach, really the way we're going to speed up the process or the first and second steps, which are the disintegration and the dissolution of the tablets, are going to be when we give that tablet with water, because basically the stomach was empty, and if we give the drug with water, basically the water is going to help dissolve and disintegrate that tablet, and also the time that is going to remain in the stomach is only going to be a few minutes, because it's going to help move that drug rapidly through the stomach into the intestine. It's all going to move very rapidly, as I say, and all the drug given is going to become in contact with the mucosa of the intestine and is going to be absorbed. So what we see in the right picture is that the solids, in other words, food, are going to stay in the stomach much longer, and if we give the drug with food, what usually happens is that the absorption is not only slower, but it is probably not going to be as complete, because much of the drug will probably be embedded with the food particles, and that way is not going to become in contact with the mucosa of the intestine. So if we look at these other graphs, they're showing how much of these drugs get into the system in humans that were volunteering to take oral tablets for each one of these medications. So if we call bioavailability the total amount of drug that gets into the system, on these graphs they're basically comparing how much was getting into the bloodstream by giving the same dose orally with 25 milliliters of water, or a big glass of water of 250 milliliters for 4 drugs: aspirin, erythromycin, amoxicillin, and theophylline. And of these drugs, only aspirin is really a non-steroidal anti-inflammatory drugs, but the idea was to show the importance of those mechanisms that I was just alluding. If you provide water on an empty stomach, you basically speed up the process of disintegration and dissolution, and also you speed up the movement into the intestine, and that is basically translated into a faster absorption and also a much greater overall absorption. Otherwise, basically the pill is not going to disintegrate completely, and is going to move into the intestines without totally disintegrating, and also being not totally dissolved. And by not being neither disintegrated and dissolved, you're not going to get a complete absorption either, which is what's happening on these graphs, as you can see here. Now, the question I was also posting earlier with regards to distribution is how does being highly protein bound affect the duration of action? Well, most of the time when drugs are highly protein bound, they cannot access the interstitial spaces, and they usually have a very low volume of distribution. In the case of non-steroidal drugs, that may have a therapeutic advantage, because when there is an inflammation, as you can see here, the permeability of those capillaries allows for the proteins to leak outside of the vessels, and you basically get accumulation of the drug in that inflammatory exudate. In other words, the concentrations of the drugs may even exceed the one that is in plasma, and may actually remain much higher even when it drops in plasma. So the practical implications of this effect are that you may give one dose of the same drug that we have on this table, and which have a very short half-life in plasma, but the duration of action is much longer, at least 24 hours, so you only need to give the drug only once a day. Obviously, this effect takes place because there is an inflammatory process that allows the drug to accumulate at that site, otherwise it would not be possible. So if we were to simply take into consideration the elimination of those drugs from circulation for each one, and to calculate the interval or the time that we need to administer the next dose, we would really have to give them a lot more than just once a day. As I say, if we just take into account the half-life of those drugs. But because they now accumulate at the site of inflammation, as we say, we don't really have to worry about that, even if they have disappeared from circulation. Now, if we talk about the next step, which is biotransformation, which other people use the term metabolism, this is going to be necessary to eliminate the non-steroidal out of the body. Unless they are transformed, as I say, they cannot go out with the urine or bile, and they would pretty much accumulate in the body and stay probably there forever. Probably I shouldn't say forever, because a small percentage, maybe 1 or 2%, goes out unchanged with the urine. In any case, as you can see here, most of them are going to follow a two-step reaction, which mostly occurs or takes place in the liver, in which the drug or the xenobiotic refers to foreign chemical of the body, are going to be changed chemically into a different molecule, which we're going to call metabolite. That metabolite may be active or inactive, and basically that metabolite usually tends to be more water soluble. It can be either excreted or through the bile or kidney, but sometimes that's not enough. It may need a further reaction, and that further reaction basically means that it needs to be conjugated with another molecule that will definitely increase its water solubility even further. So this time it can definitely be excreted. Now, the process of or the combination of the metabolism and the excretion is usually what we call elimination, because the parent compound disappears from the circulation. If we were to show an analogy of this reaction, we could show you this picture of a truck hitch trailer. The truck would be the chemical that we want to eliminate. The first thing that we need to do is either add a functional group or expose a functional group in that chemical. That functional group would be the hitch. Obviously, if the vehicle already comes with a hitch, then we wouldn't need to do through that first type of reaction. As you can see here, the chemical with the hitch may still be poorly excretable, because it does not really meet the criteria of being entirely water soluble. So you may need to go through the second phase of enzymes, which is adding basically the trailer. You hook the trailer, and once you join those two, now the whole entity is really water soluble, and it can easily be eliminated either through the urine or the bile. Now, why do I say all this? Well, the practical application is that when we have drugs that go through extensive metabolism by both reaction, one of the consequences is that there is going to be a lot of variation in the elimination of those drugs, and not only between the species but also between animals within the same species. And this is actually what applies to non-steroidal anti-inflammatory drugs. And now, the other important message that I want to convey here is that cats as a species have a very limited capacity to carry out the second phase reaction with glucuronic acid. And because of that, because they have that deficiency, they present a real challenge to clinicians, as we will see on the next video. You cannot really use these groups of drugs in general because more than one time for most of them. And if you do, you really have to space them several days because they're not capable to eliminate them. If we look at this reaction, we see that salicylic acid, which is really what actually gets absorbed from the intestine when you give aspirin, to a cat is conjugated with glucuronic acid by a transferase in the liver, and because cats are deficient in this pathway, they have a very prolonged half-life of between 1 and 2 days, as opposed to cats or humans, which have a half-life of 8 hours. And the implications is that the same dose you give in dogs every 8 hours, you have to give cats every 2 days. So that's one of the things that we'll talk in more detail on the next video. So I think this is my final slide. On the next video we'll talk about specific non-steroidal drugs in more detail. So until next time, take care and bye-bye for now.